Okay. Yeah, so again, I want to thank the organizers for inviting me to come and asking if I would give a tutorial talk. If I understood the request to be essentially the frontiers of what we know how to learn more or less efficiently. And we'll see that there is some wiggle room, a little bit of squish in terms of what we mean by efficient here. This is why this word is in significant quotation marks. So I apologize, there's not going to be any MCSP in this talk. I think there's not even going to be any meta complexity in this talk, so you can, take off and go to the farmer's market early if you want. But there will be hopefully some discussion of learning results that are potentially interesting or relevant for people who think about these meta complexity problems. Okay, so what's the roadmap? I'm going to essentially give you a two-part talk. The talk is going to be, what do they say, like a mile wide and an inch deep. There's not going to be any I'm not going to build to a striking conceptual conclusion or a big reveal or something like that. It's very much a survey. My goal is to kind of tell you about the state of the art in terms of results and open questions for efficiently packed learning, kind of fundamental bread and butter, Hall of Fame concept classes. The kinds of concept classes we often think about in fields like concrete complexity and meta complexity. So that'll be the first part of the talk. You'll notice there's also a stealth zeroth part of the talk. The second part of the talk is I'm going to be telling you about kind of, I don't know what to say, abandoning our dignity or lowering our standards. Thinking about when we say efficient path learning, typically, what most people who work on learning would think this means is polynomial time, maybe quasi-polynomial time on a bad day, something like that, mildly exponential time. For the second part of the talk, we will dig a little deeper in the well, and we'll think about learning with non-trivial savings. So learning just a little bit faster than time 2 to the n when we're looking over the development cube with 2 to the n inputs. Okay, so yeah, whether or not it's abandoning our dignity, that's kind of up for you to decide. The talk is going to primarily have an algorithmic focus. Again, it's going to be a high-level survey where I tell you, hey, this is how well we can learn this thing in this model, and maybe 2 words about the techniques. This is how well we can learn this thing in this model, so on and so forth. So that's basically the roadmap. I'll talk about the zeroth part in just a second. There are many things I won't discuss, so I'm not going to talk at all about noisy learning problems, agnostic learning, other forms of learning in the presence of noise. It's a huge topic, a great topic, but it's not going to be part of this talk. I won't talk about learning over any domains other than 0, 1 to the n, okay, so we can rest secure in the knowledge that 2 to the n means you've failed, you've not done an impressive job at non-trivial learning. So with apologies to Ilya, I'm not going to talk about, for instance, algebraic models or algebraic results. I won't talk about continuous settings, learning over, Rn, Gaussian distributions, nothing like that. It's going to be very Boolean, 0, 1 to the n oriented. I'm just getting nervous that I'm about to erase things. Okay. Yeah, so I won't talk about that. I won't talk about that. I won't talk about many other things. What will I talk about? I have to start by telling you about a number of different learning models, because if we want to think about the state of the art is very different depending on kind of precisely how you define the rules of the learning field. Okay, so that's the part 0 of the talk. I have to give you some background and explain a couple of different models. And we'll see the landscape really changes in a kind of significant way depending on exactly what framework you're in. Okay. Oh, the last thing I should say before I get into part 0, please, let's make this super informal, super interactive. If you have a question, just speak up or shout out or whatever. Okay. So far, so good? Good. All right, so let's get into it a little bit. The first model that I want to tell you about is the so-called distribution-free path learning model for path learning and concept class. It's a little different than the framework that Marco sketched for us in his talk yesterday. From what I remember of yesterday, which feels like a long time ago, you were talking about uniform distribution learning, and you were talking about learning with kind of just non-trivial advantage, getting accuracy 1/2 plus some 1 over poly n for learning your function class. So we're going to be thinking, at least for this first model, about a more challenging framework. Okay, there's an arbitrary distribution, an unknown distribution. The learner doesn't know what it is, and it could be anything. So it might, really be concentrated on images of cats, or maybe a mixture of images of cats and images of Dungeons and Dragons characters, or something like this. So there's an unknown distribution over here. Okay, the learning algorithm's form of access to the function it's learning is f, is that it gets independent, random, correctly labeled samples. Okay, so it presses a button, it gets this x, f of x pair. X is the n-bit string, f of x is the single binary output of the function that's being learned. Okay, I think I left off the important thing here, but I didn't mention, whoops. Oh, like I said, I tend to erase things when I said. I didn't mention what is a concept class. A concept class is just the class of functions you're thinking about learning. Right? If it's the first lecture of your learning class, your concept class is Boolean conjunctions or something like that. If you're super ambitious, your concept class is polynomial sized circuits. spoiler, we're not gonna have state-of-the-art results for that because we don't think the non-trivial equation. Okay, good. So we're interested in, you have an unknown function f, it belongs to the concept class, okay? Your form of access is you get random labeled examples, where again, the examples are distributed, they're IID drawn from this unknown distribution, okay? And our goal is to do probably approximately correct learning. We want it to be the case that with high confidence, probably 1 minus delta, and this is a probability over the randomness of the algorithm, and sorry, any internal randomness of the algorithm and the randomness from getting distinct samples, okay, from this label. So we want with high probability, I'll put a high accuracy hypothesis, a hypothesis H, which, you know, is wrong if we draw fresh examples from that distribution. Those random examples would probably be most epsilon. Okay. And just a quick word about what does it mean to kind of do, you know, what is the running time and the efficiency of a learning algorithm in this framework? Well, it should obviously be the amount of time that it takes us to, you know, cook up the hypothesis, but it should also be the amount of time that it takes to evaluate the hypothesis on a fresh input. You can't get away with learning efficiently, you know, putting this in, you know, ironic quotation marks, by drawing a bunch of examples, memorizing the examples, and then offloading all of the work onto the actual evaluation of the hypothesis. That wouldn't be fair. So a pretty standard model. This is probably familiar to many of you, most of you, potentially all of you. And one thing I'll mention is, you know, you might say, oh, this model looks ugly. I have to think about the accuracy parameter, the confidence parameter, epsilon, delta, there's all these things floating around. You don't actually need to worry about dependencies on either of those parameters in this distribution-free PAC learning setting, right? So if you want to think about like achieving a certain level of, let's say, confidence, learning to accuracy 1 minus delta, if you can learn to confidence 1 minus delta, if you can learn to confidence 3/4, you have a 3/4 chance of outputting a good hypothesis, it's easy to amplify that. You just run your algorithm log 1/delta many times, you'll get a bunch of hypotheses, almost certainly one of them will be good, and you can then test that hypothesis on a fresh batch of data, and you'll test the hypotheses on a fresh batch of data, and you'll be able to identify a good one. Okay, so there's really never any reason to think about the dependence on the delta parameter. It's always like log 1/delta. And thanks to the theory of accuracy boosting, which I guess Russell was going to tell us about for smooth boosting algorithms in the afternoon, we also never have to worry about the dependence on epsilon. If you can achieve 51% accuracy, you can achieve 1 minus epsilon accuracy with the dependence that will only be inverse polynomial on 1/epsilon. Okay. So the model's not as messy as it looks in terms of the dependence on epsilon and delta, having to think about how things go there. But if you say, you know, it still seems a little complicated, there's this distribution, these parameters are there, whether I have
Sorry, I have a question about this.
Yeah.
I want to discuss epsilon and delta for just a couple of minutes.
Nothing about more than discussing epsilon and delta.
So yesterday, I definitely screwed up, turning an arbitrary distribution into the uniform, and then turning, high accuracy into barely better than a coin toss.
You didn't screw up at all. You made choices which were right for you at the time, but you know.
But I'm not sure that I limited epsilon and delta correctly, because when I'm looking at this model, I'm always thinking in terms of you need to compute the runtime of a PAC learner in this model in 1/epsilon and 1/delta. Is that equivalent to what you said about
When
the
you say
evaluation?
compute the runtime, I mean, usually what happens is someone breaks down an algorithm, they analyze the algorithm, and they say, hey, the running time of this algorithm for epsilon delta PAC learning is polynomial in, you know, 1/epsilon, n to the log n, or whatever the dependence happens to be because of the particular concept class, and log or polylog 1/delta. And if in this model, they give you a different running time, which doesn't have like a 1/epsilon and a log 1/delta dependence, then you kind of smile and pat them on the back and say, you know, you contribute, you achieve the log, the poly 1/epsilon log 1/delta dependence. Yeah, in this model because of boosting accuracy and boosting confidence.
Okay.
Yeah. Does that make sense?
Yeah, that's perfect. So that's just a feature of most analyses and not a feature of the model at all.
I mean, it is a black box statement. The following statement is true. If you can PAC learn a concept class in time, let's call it t of n, where I fix the accuracy to be delta equals 0.1, and I fix the confidence, sorry, the accuracy epsilon to be 0.1, the confidence delta to be 0.1. If you can learn in t of n time then, in that setting, to 0.1 as these parameters, then you can learn to epsilon delta as these parameters in time 1/epsilon times t of n times log 1/delta. Yeah, that's the black box statement.
Thank you.
Okay, good question. Good, so if you don't want to have epsilon delta conversations, again, I love epsilon delta conversations, but if you don't want to have them, you can think about an essentially equivalent model. Now, it's provably not equivalent. There's this nice paper by Bob Blum from the early 90s where he gives a cryptographic separation. There is a concept class which is efficiently PAC learnable, but not efficiently learnable in this model, but it's artificial. For every concept class you're going to encounter in your day-to-day life, you can think about this model and, it's the same thing. It's a strictly harder model, but in practice, it's equivalent to the PAC learning model. And this is a very clean model called online mistake-bound learning. You can also describe it as learning just from equivalence queries. And you just think of it as a repeated game that the learner plays with kind of nature. Okay, the learner maintains a hypothesis function. It's the same basic setup. There's a concept class which you're trying to learn. There's an unknown target concept in that class. And the learner maintains a hypothesis at every round of learning. Learning proceeds in rounds. In a given round, how does it work? The learner's like, hey, this is my hypothesis. Is it exactly correct? Is it, perfectly equivalent to the target concept? If so, you're done, right? You've learned correctly. If not, you get a counterexample. You can think of this ultimately as like you make an equivalence square. You say, am I completely right? And if you're not completely right, you're given a point where you're wrong. You can also think of this like an online setting where we're counting how many mistakes you make as you go. Okay, and we only pay in terms of running time for the rounds where you make a mistake. So the goal of this setting is to, have an algorithm which is efficient in terms of evaluating the hypothesis, efficient in terms of updating the hypothesis when you get new information, and has a small mistake path. That's an efficient algorithm if we want to make this. Does it make sense?
It seems like you learn the function exactly.
Excuse me?
It seems like you learn exactly.
This is an exact learning model.
But it's kind of the model rather than how you would actually use it, right?
It's
So
more, yeah.
Yeah, so what you use it is, you use this algorithm, and as long as you're not seeing any mistakes, you pretend that you've got then it'll work exactly. As soon as you see a mistake, it's kind of like science, right?
Exactly. Yeah. That's a good way of putting it. So if you have a learning algorithm in this model, you get a path learning algorithm. You just, right, instead of asking, no, am I perfectly correct? You draw a bunch of examples, 100 over epsilon examples. If you got them all right, hey, congratulations, you're epsilon accurate and you achieve the path criteria. Yeah. And in practice, I think almost without exception, when we have a learning algorithm in the PAC model, except for this bizarre pathological thing that Hoffman cooked up in the early 90s, somebody eventually converts it into a learning algorithm in this way. So take your pick, whichever model you like to think about.
So is every concept in C, the concept class efficiently computable?
I mean, the concept classes that people think about on the ground are concept classes like decision trees.
What you're talking about?
Yeah, I mean, you can think about whatever concept class you're interested in. It would be very weird to be thinking about concepts that are hard to compute, I think.
Okay.
Yeah.
I'm saying it needs to be efficient, everything in C needs to be efficiently computable to be able to do this, right?
Yeah, I suppose that's true, yeah.
I mean, you end up with H equals F, right?
Yes.
And
People
H
don't
needs to be
typically
efficiently
think about learning concept classes which are hard to compute, which contain concepts which are hard to compute, yeah.
Okay.
Yeah, no, that's a good point.
Oh,
Yes.
yeah, question. In the spirit of what was discussed here, this H equals F is like, we call exact learning. Like, what happens if you miss F by a single point?
Then you'd get a counterexample, which would be that point.
Okay, so
I thought you guys would like this model. If you don't like this model.
No,
just
we
think about it.
really don't, no, I like this model, it just, I was, okay. I just always thought of it as a stronger model than PAC, and I was kind of surprised that you think that almost all the PAC algorithms can be put in this model.
I mean, I just know literally one example, which is a contrived example for the
Yeah.
purpose of separating.
Yeah.
Yeah.
Given the contrived example, is there any way to formalize that? To say like online mistake bound and PAC are the same unless the concept class has this particular horrible feature enjoyed by the pathological? Do you see any possibility of that happening?
I mean, not clear to me. The contrived example, it's like a cryptographic construction based on one-way functions, where the way I try to explain it in class is it's like a flashlight which works in one direction. If I point it in this direction, it lights up the room. If I point it in this direction, it doesn't work. And so like if you have a big data set of examples that you've drawn, well, think of them as like ordered, and you kind of use it on the rightmost example. I know you can light up almost all the examples you saw, but in an online setting, the ordering of the examples, they can be given to you in the other direction, so you keep on getting examples where you can't use your flashlight. I don't know, I haven't thought, I don't know if anybody's thought, I'm not sure if you're productive use of time to think about like formalizing the property of a concept class, which means that you can separate. Yeah, this is the weirdest audience I've ever had. That's great.
This is going off on the same tangent, but, so how about statistical query algorithms?
Yeah,
Can they all be simulated in this model?
in this online model,
Yeah,
they can be simulated in the PAC model, and if you
Right.
can learn in this model, you can learn in the PAC model.
right, but saying like non-pathological PAC algorithms, to
Yeah,
me suggest statistical query algorithms.
well, I mean, is parity learning pathological?
Is what?
Is parity learning pathological PAC algorithm?
I don't know,
I don't know either.
but,
Discuss that.
well, it's different from the most, yeah.
Yeah, definitely wants to know. Zach, you have a question?
Yeah, let's just say the concept class is a singleton.
One concept.
Yeah, of like a function that's hard to compute efficiently, but has good approximations that are efficiently computable.
Yeah.
Then can't you do PAC but not online?
Okay, so maybe I should, no, you're pointing out, yeah, kind of implicit assumptions that people typically make here. Typically, people are only interested in learning concept classes that contain efficiently computable functions.
No, that only consists of efficiently computable.
That only consist of
Yeah.
efficiently computable functions. Yeah, that is a good point.
Okay.
Your stress testing this definition is if you go.
Well, I'm just trying to understand, okay.
Yeah,
And do you insist that H belongs to C in the PAC model or no?
it's not required. That's called so-called proper learning.
Yeah.
Yeah, that's
Okay.
nice if you can do that, but you don't have to do it. Yeah, good question. Okay, let's move on to a different model, uniform distribution PAC learning. This one basically we saw yesterday. I don't have to say very much. You only have to worry about the case where the unknown distribution, we're back in the distribution setting, is uniform. Okay? And in this setting, if you want to think about efficient learning, you do have to consider the dependence on the epsilon parameter, the error parameter. And you see example here is like the class of monotone Boolean functions. It's very easy to learn them with a small advantage, with advantage something like 1/n, or you can get even log n over root n, whatever. But it's provably not possible to learn them in polynomial time if you want to learn to accuracy 99%. Okay? And so it's not the case that you can sort of automatically do this accuracy boosting in the distribution free setting. You have to pay attention to epsilon. We'll see if we get to this part of the talk, we'll see epsilons all over the place when we talk about non-uniform distribution results.
I know that Tom is not talk about agnostic learning, but like if you were to talk about agnostic PAC, would you have some kind of equivalence to some version of online, or that goes away if you allow noise?
Things are weird in the online setting if you allow noise, because you're never gonna get this perfect consistency. It's a little, yeah, another good answer.
It's not as clear.
Another quick answer, yeah,
Okay.
good answer.
Thank you.
Okay. Okay, we're almost done with part zero. The last thing to think about, because we talked about this in various settings, is all these models, the uniform distribution model, the regular path model, the online model. If you want, you can give the learner more power by saying, you get black box access to the function. You can make so-called membership queries. Okay, so instead of getting a random example, pressing the button, or getting a counter example to your current hypothesis, you can say, I really want to know what is f of this particular point that I'm choosing. Okay, so you're strengthening the model, and we'll see that known results typically become stronger when you have that kind of additional power. Okay, so we're up to part one, state of the art for efficient learning algorithms. And then again, this is going to be a high level tour, but stop me whenever you see something that's interesting. To help us keep things straight, when you see green text, it means I'm telling you about some good news, a positive result. I think I'm only giving you state of the art positive results for these different classes. And when you see red text, it means it's a challenge, it's a frontier, it's someplace where we have a question, we don't know whether we can do something or not. Okay, so first model, distribution-free PAC learning. If you had to go to a desert island with one distribution-free PAC learning algorithm, you would definitely want it to be polynomial time linear programming. Okay, this is a powerful algorithm. It gives us state of the art for a bunch of concept classes. In particular, it tells us, almost a retranslation of this phrase, polynomial time linear programming, that you can learn linear threshold functions, functions of the form is w dot x greater than or equal to theta, one if that's the case, and zero if that's the case. You can learn functions like this in polynomial time. And just a one-line kind of little illustration, if you get an example, which is something like your string is 10010, and you're told, hey, this is a positive example, Well, that gives you a linear constraint on the unknowns, on the W and the theta, right? Since it's 1, 0, 0, 1, 0, it tells you that W1 plus W4 is greater than or equal to theta. So a collection of labeled examples give you a collection of linear constraints. Linear programming tells us that we can find a feasible solution, and generalization theory tells us that a feasible solution to a sufficiently large set of examples will have high accuracy and high confidence. Yeah. High level, but it's all good. It's all very standard. Okay, well, if you can learn LTFs, linear forms, these are just degree 1 polynomials in polynomial time and polynomial number of features or variables. You can learn degree D PTFs, polynomial threshold functions. So functions of the form, I have a degree D polynomial and I output 1 or 0 depending on whether or not it exceeds some threshold in time polynomial and n to the d. Because the degree D polynomial is just like a linear form over kind of meta features or expanded features or monomials. Makes sense? Nothing fancy or complicated, just a feature expansion. So this tells us that, if you have a community of people who are interested in proving upper bounds on PTF degree for different classes of functions, that translates with 0 work into getting, more or less efficient, depending on how good those degree upper bounds are, learning algorithms for those classes of functions. And this is responsible for the state of the art for really almost all concept classes in the, vanilla PAC learning model. So, I don't know how much time we want to spend on these particular applications, but if you want state-of-the-art results for PAC learning decision trees, there was a previous kind of ad hoc algorithm by Ornthorpe and Hausler. You can recover it by doing a simple analysis to show that if you have a poly-size decision tree, it's computed by a log degree polynomial threshold function. There's a polynomial of degree log n whose sign agrees with the output of the decision tree anagram. Okay. So the PTF is log n, you get into the log n time learning. For DNF formulas, we know that poly-size DNFs have PTF degree about n to the 1/3, so you get n to the n to the 1/3 running time for DNFs via this approach. This is based on like a little bit of kind of combinatorial ad hoc stuff and extremal polynomials like Chebyshev type polynomials to get you an kind of a square root and savings there. Other kinds of polynomial approximators come into play for a different concept class, intersections of half spaces. So I'm being a little maybe too telegraphic here. When I say weight W half spaces, I mean linear threshold functions where we think of each of the coefficients as being an integer, and the sum of those integers is W. So like LTFs with integer weights, and the weights are not too big. The weights are W. If you have an intersection of 2 or say a constant number of half spaces like that, there's stuff from like rational approximation, using like rational functions to approximate functions like the sine function. We have PTF degree bounds of log W, and so you get fairly efficient learning in time into the log W for classes like that. And finally, if you want kind of something which is getting a little more general, if you have the class of size S De Morgan formulas, there was a sequence of works in quantum computing showing that you can evaluate a size S formula with quantum algorithm using only root S queries. The random connection between quantum query complexity and approximate degree, which is stronger than PTF degree, tells you that you have PTFs of degree square root S for any size S De Morgan formula. So we get a result like this. Okay. So it's a pretty versatile hammer. It gives us these best known results for a number of classes like this. Yeah.
Are there any like fine-grained lower bounds on these running times?
Fine-grained lower bounds on these.
The conditional lower bounds. Like under strong ETH or something like that.
I think Leon has some recent work on some of these results. I don't know if they go all the way down to decision trees and DNFs. Yeah, I'm not sure. It's a good question. There is like a whole body of like lower bound work, conditional lower bound work. It was all this work that we talked about a little yesterday. It's like the Emmett Danieli line of work, but I don't know how close you get to matching these types of results. Yeah.
At least for decision trees, the parallel of automatability of tree-like resolution, there's I think under randomizing features like that into the logins.
Okay, so you're saying this is essentially short for decision trees?
I don't know if it exactly translates to decision trees, but the proof complexity one, which the analogy is automatability and plugin side.
Okay. Yeah, good question. Yeah, so there are a couple of other sort of, I don't know, I don't want to call them ad hoc. Like this approach is not really ad hoc. We talked about it a couple of times yesterday. If you don't have noise and you're trying to learn, say, just parity functions, linear polynomials over F2. You can do this by solving a system of equations like Gaussian elimination over F2. Okay, and you can generalize that if you have a degree D polynomial, you know, you just expand, you have n to the D features, you can learn n to the D time degree D F2 polynomials, and even we can handle S sparse F2 polynomials and something like 2 to the square root n time. This is by kind of combining with some combinatorial decision tree building approach, sort of from the DNF work.
And where's S?
Excuse me?
You said S sparse, and
Oh.
you said a bound with no S.
Yeah, let me fix that for you right now, Zach. I didn't want to disappoint.
No,
Yeah, sparse, yeah. So if I had an S there, it would be like 2 to the root n log S.
Okay.
Okay, yeah. Good. Okay, so what about some things we don't know how to do? What about some challenges at this point? We don't know how to learn an intersection of two arbitrary half spaces. This is kind of annoying. It's been like a sort of big open problem for many decades. We don't have 2 to the little of n time algorithms for learning an intersection of two LTFs. It's an n of two half spaces if the weights are allowed to be arbitrarily large. In general, if I give you arbitrary half spaces, the weights could be as big as like n to the n, or basically n factorial. And so if you take the log of n to the n or n factorial, you can see that this is not going to give you anything non-trivial. And we don't have any non-trivial approaches for this problem. So that's regrettable.
Is there hardness for proper wording for this, or?
Yes, I believe there are hardness results for proper learning for this. I'd have to go back and remember more clearly, but I think that is the case. In fact, I think fairly strong things are known if you want to learn an intersection of two half spaces by an intersection of many more half spaces, some constant number or something, you still have hardness results, but I don't think we have such strong hardness results as to say that you can't do it in time 2 at the lower end.
Yeah.
I don't think they go that far. Yeah. Another class which we don't know how to handle is, say, depth 3 circuit. So depth 2, we can do 2 to the cube root n. We don't know how to get depth 3 and anything better than 2 to the n, essentially. And there are some really nice sequences of works, pretty technical works by Shurstoff, where he gives bounds on the polynomial threshold function degree of concept classes like this. So we know that, Shurstoff can write down 2 half spaces for you so that their intersection requires PTF to be linear in n. Okay, so we know that these approaches are not going to get us what we want for the PTF approach isn't going to work in this class, and I don't think they have linear and lower bounds for depth 3 circuits, but they can, periodically Sasha writes another paper and pushes these lower bounds up for the shallower and shallower circuits. So yeah, so it's not clear what an approach would be.
Are there any loopholes like where you could introduce like nonlinear variables as extension variables and then?
Yeah, you can do things other than monomials and so on.
Right.
Yeah, there is a little bit of recent work along these lines, which I'll actually mention a bit later, at least a different problem. Yeah. Okay, let me tell you about a different model. We'll augment this model. We're still in the distribution-free setting, so it still is this fairly challenging setting, but now we'll give the learner the ability to make membership queries. Okay, so it's we're empowering the learner and making hopefully we get some more positive results as a consequence of this modeling choice. The first sort of piece of evidence that, giving membership queries does make the problem significantly easier comes from thinking about monotone DNF formulas. So if you think about it in the original PAC learning setting, it's an easy sort of fact, it's a homework exercise that learning monotone DNF formulas is really just as hard as learning general DNF formulas. Right, and this has to do with the fact that the original PAC learning model is a model where it's distribution free. You have to succeed for any distribution. So if I have a non-monotone DNF formula, well, I can think about like it's a formula over n variables. I can think about writing down a monotone version of the formula over 2 n variables. I just basically take every example and I reduplicate it with fresh variables which negate each of the variables in the original form. Right, the original formula now will become like a monotone formula in the new setting. And if I had a good algorithm for learning monotone DNF formulas, I could use it and get a high accuracy hypothesis in the original setting. So if you don't have queries, we think the best we can do for if you don't have queries, the best we know how to do for learning monotone DNF is this 2 to the n to the 1/3 kind of thing that I mentioned. If you do have queries, then learning monotone DNF is trivial. And I think it kind of explains itself with a picture like this, right? So initially you say, okay, maybe the function is the constant 0 function. I think it has no satisfying assignments. You get a counter example, you get a satisfying assignment. So you get a point like this, and then you just start flipping 1s to 0s. You walk down a hypercube as long as you stay in satisfying assignments. Whoops, I walked out, I better not do that, I better come back and keep walking down. Right, so you just greedily flip ones to zeros, starting from a satisfying assignment. If it's a monotone function, well, you're gonna land at a min term. The min term exactly is one of the terms in your monotone DNF. So now you have a better hypothesis than the initial one, which was the constant zero function. You have this as your hypothesis. You say, well, maybe it's a one-term DNF and this is it. If you get a counterexample, it's going to be a point over here. And again, you can start walking down and find another term. Okay. It's really a trivial learning algorithm if you have this power to make queries that lets you do things like wander around the cube and try to find useful points, in particular these min terms, so on and so forth. So does this make sense at a high level? The monotone problem is easy? Good. Okay. There are many other things you can do with membership queries, which are not as sort of trivial or obvious as just this kind of walking down the cube kind of thing. So an old result by Dan Angler, I guess, back in the 80s is that if you have membership queries in this exact setting where we get, these counter examples, this online setting, if you augment it with membership queries, you can learn finite automata in polynomial time. If you have an automaton which accepts only n-bit strings, keep everything clean with poly n states, deterministic finite automaton, you can learn that in poly n time.
If you have equivalent query, just equivalent query, how does it compare with the membership query?
Good question. So having just equivalence queries, I was encouraging you to think of this as basically being like the PAC model where you have the distribution and you get random examples. If you just have membership queries like with no equivalence queries,
Or equivalent with no membership?
I mean, I wouldn't. So, okay, there's three things we can compare. We can compare equivalence, we can compare equivalence plus membership, and we can think about membership. Which one are you interested in?
I was the first two.
It's more powerful. So I would encourage you, like all the results that I was talking about before, up here, the stuff for PAC learning, everything I said, that we can learn this class and this time, this class and this time, et cetera, et cetera. You can think of these as all results which go through for this model of learning just from equivalence queries. Yeah, but the point of the current section is we have more powerful results when I say you don't have just equivalence queries. If you get equivalence queries and membership queries, that's what I do with that handwriting. That's like the model that I'm in now. If I have both equivalence queries and membership queries, I can do monotone DNF, I can do finite automata, I can do a bunch of other things.
You still need equivalence queries.
You still need equivalence queries, yeah. So that's a great question. Let me draw you a picture to convince you that if you only have membership queries, if that's all you get, you can't do much. For instance, you can't learn linear threshold functions. Here's why. I'll promise you that your linear threshold function, sorry for the crude drawing, this is the Boolean cube. I promise you your linear threshold function is the majority function, except it also includes exactly one point, which is one level below the middle layer.
Oh, yeah.
Yeah. It's not hard to write
Or
this as
even conjunctions of variables. And maybe that's even simpler, right?
point functions. Yeah, there's lots of things. There's lots of things you can do.
Finite automata, I guess.
Yeah.
Yeah, there's lots of things you can't do. There are cryptographic hardness results for learning finite automata. If you only have random examples or equivalence queries. So yeah, like this is like a real strengthening of the model. It is like, bona fide stronger. We have lots of evidence, both in terms of the things we can learn, both in terms of known hardness results. Yeah, that getting the membership queries makes us stronger. But if you only had membership queries without the equivalence queries, there's not much you can do. Yeah. Good question. Okay. Good. So decision trees. Let's talk about decision trees for a minute. Like I said, in the model of only equivalence queries or PAC learning, we only have quasi-polynomial time results. And we're saying that, there even are maybe some lower bounds suggesting you're not going to be able to get polynomial time results if you don't have queries. If you do have queries, you can learn polynomial size decision trees in polynomial time. This is going to be my cop-out throughout this talk. Whenever I don't have a good way of saying something, I don't know it well enough to summarize briefly. It's like ad hoc techniques. So using ad hoc techniques, Nader Bashuti gave developed this monotone theory for learning decision trees in polynomial time, and there's kind of a broader, more principled approach based on multiplicity automatas. This is some generalization of like the Angler and automaton style learning stuff, which you can use to learn decision trees in time polynomial in their size and the number of variables. So again, like stronger results than we can achieve without the membership queries. Another class that we can learn is, remember in the PAC setting, I said if I have polynomially sparse F2 polynomials with no constraint on the degree, we said there's something like a 2 to the root n time learning algorithm. If you don't get the membership queries, but if you do get the membership queries, then it's known that you can learn these in polynomial time. This is Shapiro-Selly. I'll again call it an ad hoc approach, but you can get actually something even stronger than this from this multiplicity automaton type result. You can get a parity of, I think, polynomially many arbitrary conjunctions. They don't just have to be monotone conjunctions. And F2 polynomial is what? It's parity of a bunch of monotone conjunctions. You can handle even parities of non-monotone conjunctions using this multiplicity automaton style approach if you get the queries. Okay. So the evidence is mounting that membership queries do make the model stronger. Let's see. So yeah, we told you a little bit about DNF formulas in this setting. You can think about the DNF learning problem, like the results I was telling you about before. This was like, this was like S equals poly n. And we had time like 2 to the, sorry, this doesn't work so well with the recently. We had S equals poly n. And we had time something like 2 to the n to the 1/3, maybe leaving off some log factors, something like that. This is state of the art, the result I told you about before. If you think about DNF formulas with, a largish number of terms, some polynomial number of terms, S equals poly n. Another regime you can think about is, I think S is very small. S is 5, or S is log n, or something like that. You don't, unfortunately, the result I was telling you about before doesn't do any better if you have a relatively small number of terms. If S is small, until very recently, the state of the art was polynomial time in n and 2 to the s. And there were like 3, 4, 5 different approaches that did this. Blum and Rudich was, I think, the first one. You can do this using automata. You can do it using the monotone theory. There are a bunch of different ways of getting a running time like this for DNF formulas with a relatively small number of terms. Like I said, one of them is based on automata. The other ones I'll call ad hoc, sort of combinatorial approaches, which in some sense, the Blum-Rudich one, it did something like what Russell was describing. You sort of muck around in the cube and make some queries and you look for features, which will be useful features to put together the DNF. So very, very recently, it's possible to make an improvement on this. You can get it to be polynomial in n and 2 to the square root s time. This is joint work with Josh Ullman, Shubham Nampally, and Shalom Patel. And basically what do? You combine these, what we call them ad hoc approaches, or these, coming up with new features type approaches with some of the technology which was used to get like the 2 to the n to the 1/3 time DNF learning. Some of these like Chebyshev polynomials let you get some square root savings kind of thing. And it's when all the dust settles, it turns out that we can do better than this. We can get something like, instead of being able to learn, I guess, log n term DNF in polynomial time if you get queries, we can basically handle log squared n term DNF in polynomial time now if you get these kinds of queries. Yeah, so one other very recent result, which is for kind of a bizarre class, is this class of exact DNF formula. So I don't think people studied this before, but this was the class that our techniques turned out to be useful for. So what is this class of exact DNF formulas? It's DNF formulas in which all the terms have the exact same length as each other. Okay, so this is a non-trivial restriction on DNF formulas. If I have a general DNF, it might have one term of length, I don't know, log n to the 10th, and one term of length square root n. And if it's a distribution independent setting, maybe the term of length square root n is just as important. It's satisfied just as often as the much shorter term, right? So I don't know how to handle DNFs like that, but if you promise me that all the DNFs have the exact same length as each other, then it turns out it's possible to get quasi-polynomial time via this kind of newish approach based on random walks. Like you do a random walk essentially on the satisfying assignments of the DNF, and you don't do the random walk until you achieve like mixing, because that might be a really long time. You do a random walk until you haven't fully mixed yet, but you've mixed enough that you'll be able to, if you get lucky, identify one term. And it turns out that being able to identify one term, if you're in this setting of these exact DNFs, you can do some more work, and you can actually come up with an algorithm that actually learns the DNF. So like a little bit of recent progress on DNFs, but we, even with membership queries, we still seem to be not particularly close to really getting a polynomial time algorithm. And I don't have it on the slides, but there's this very interesting work by Anglin and Karatonov from the 90s, this paper called When Won't Membership Queries Help? Where I think what they do is they show that under some cryptographic hardness assumption, if you have a polynomial time algorithm for learning DNFs with membership queries, you'll also get a polynomial time algorithm for learning DNFs without membership queries. So you might view that as a barrier, which says, hey, like these improvements, they're probably not going to go all the way to getting you polynomial time. But it's not clear kind of how far you can go at this point for DNFs. Okay, so this part's a little sad. The challenges and open questions in this more powerful model, the model where we get membership queries, but we're still trying to learn with respect to arbitrary distributions, or think of it as equivalence queries. Those are the exact same challenges that we had when we didn't have the membership queries. We still don't know how to do anything, kind of really non-trivial to the little o of n for learning intersections of even two half spaces. We still don't know how to do depth 3 circuits in time 2 to the little o of n. So we don't know how to take advantage of having membership queries for those problems. Okay. I'm sensing a bit of a down vibe in the room, and that may be because we have all these challenges with learning. So let's go ahead to like an easier learning framework where we have like a nice structural result, which you just promise me your function class satisfies this structural condition, and you get learning results like as easily as falling off the log. Okay, so this is uniform distribution learning. At this point, we won't have membership queries. Life is going to get even better. In 5 minutes, I'll give you membership queries and the uniform distribution, and then like we'll have some more stuff. Okay, but for now, we're retrenching a little bit. We gave up our membership queries, but we're only trying to learn with respect to the uniform distribution. Okay, and we are going to see like epsilons all over the place in terms of the running time dependencies, because that's life under the uniform distribution. So there's a nice principled approach here, which is it's kind of a generic tool, the same way you can really think of it as like it's a different statement about polynomial approximation, right? The thing about PTF degree earlier was that for arbitrary distributions, if your class of functions can be approximated in this, somewhat weak sense that you just have a low degree polynomial which gets the functions, whose sign is correct for your function everywhere, right? So kind of that weak, sign approximation of low degree polynomials gave you learning. That was what we saw in the distribution free setting. Now, this Fourier concentration stuff tells us, hey, if you have like low degree polynomials, which are L2 approximators, so a stronger type of approximation, or a different kind of approximation for functions in your class, then you get uniform distribution learning algorithms in kind of this automatic, straightforward way. So if you're not familiar with the Fourier notation, this probably isn't going to do much for you, but if you are familiar with it, right, we write our Boolean functions as f equals like a sum of Fourier coefficients times basis functions. And so, if most of your Fourier weight, right, for a Boolean function, we think of the sum of the squares of the Fourier coefficients, the total Fourier energy is being 1. If most of that weight, 1 minus epsilon of that weight is on low degree coefficients of degree at most d, or probably the most epsilon weight above degree d, then you can learn to accuracy epsilon. It's really just like L2 polynomial, you think of it as like a simple regression algorithm. You just estimate each of those Fourier coefficients. There's only n to the d in front because we have this bound. We're just going to be estimating Fourier coefficients of degree up to d. You just estimate each of them to sufficiently high accuracy, and you'll learn to accuracy epsilon, or maybe 2 times epsilon, or something like this, under the uniform distribution. Okay. So again, it gives us a recipe. If you want to prove that a class of functions is uniform distribution learnable, don't think about learning. Go off in the corner and prove a Fourier concentration result. Again, that's been very successful. So yeah, you look troubled.
Yes, it's not neglecting stuff, so do you neglect the equivalence queries here as well?
There are no equivalence queries in this model. This is uniform distribution learning. So the way learning works in this model is I have a button, I press the button, I get a uniform random example, and the label of the function on that example.
So if you add equivalence queries, you're going to get something very powerful or what?
So you're saying you add equivalence queries and you want to.
So you push the button, but I also allow you, I'm also asking you, is this the correct thing, right? That's the
So
thing.
you want to be perfectly correct. I mean, you'd be done if it was only epsilon approximately correct, but not. Like, I think I could just, like, if you say to me, okay, you have the power of this equivalence oracle, I can just press the random example button 100 over epsilon times, and I'll either get a counterexample serving the role of the equivalence
Only if
oracle.
they're far away, not if they're close.
Sorry?
Only if they're far away, they're epsilon far, then yes, you can put
Yeah,
the random
but if
button.
they're epsilon close, I'm done. Like my criterion for successful learning in this model is I output an epsilon accurate hypothesis under the uniform distribution.
But Okay, so I don't need that, basically I don't need it.
You don't need your equivalence oracle, yeah, so you sort of, it's like nature provides or something, right? You're given like the kind of oracle which you need for the success criteria that you have for this model. Okay, that makes sense? Okay, good. Yeah, so some great Fourier concentration results of our time. Lineal Mensur and Nissan in the same paper in which they introduced this like low degree algorithm, low degree learning approach. They use the switching lemma to prove that AC0 circuits have pretty good Fourier concentration. And this was refined over the years. Hastad proved a better bound. Abishai-Tal eventually got like a really the best possible bound. And so you can see like, you know, basically if you see it in the exponent, it means it's the Fourier concentration. It's the value of D that you have to go up to achieve, you know, 1 minus epsilon of the Fourier weight below level D. And I'm showing you these fairly specific, you know, dependencies here. Instead of fixing epsilon to be, you know, 0.1 or something and reducing the number of parameters, both to drive home this point that, you know, the epsilon dependence is something you have to think about in the uniform distribution setting. And also because when we go to the learning with non-trivial savings kind of thing, these epsilon dependencies will actually turn out to be important in terms of the types of results that we're able to get. We'll see more about that in a little bit. So yeah, so what do we know? Like, you know, AC0, you have a result like this, your Fourier concentration at level is basically polylog n. Monotone functions, a simple argument shows that any monotone function has Fourier concentration, all but epsilon of its Fourier weight is on coefficients of degree at most root n over epsilon. Okay, so we get non-trivial, you know, sub-exponential time learning for this very rich class of all monotone functions under the uniform distribution.
Wait, what do you mean that the Fourier stuff is at most root n over epsilon? What does epsilon have to do with the Fourier weight?
What I'm saying is that if f is, maybe switch to something else to ground. If f is monotone, then the sum of the weight of the Fourier coefficients above level root n over epsilon squared is less than epsilon. Does that make sense?
Yeah, sorry.
Okay, good. Okay, good. Good. So just a quick sentence on, you know, sometimes to prove these Fourier concentration bounds, you do switching lemma kinds of things or other types of analyses. Sort of a cute technique is to use noise sensitivity. So just to throw a couple of words out there, noise sensitivity. What does this mean? It means you pick a uniform random x, okay, and then you take a noisy version of x. So this n sub row of x means you flip every bit of x with probability rho. And you ask yourself, what's the probability that under, you know, random x and a random noisy version of x, the value of the function changes? This is something which would be trivially easy. It's a calculation to figure out what this is for a parity function. And Fourier analysis means you think of your function as a linear combination of parity functions. And so you can capture this quantity is closely related to the Fourier concentration, how much of the weight is on small parities, medium-sized parities, large parities, so on and so forth. Okay. So, you know, maybe if you go off in the corner and you can combinatorially or analytically bound this quantity, it tells you something about the Fourier concentration of a class of functions. So this is the worst way ever, I would say, to learn linear threshold functions. A nice argument of Perez from around 2001 or so, where he shows that the noise sensitivity of noise rate epsilon, sorry, I shouldn't be using epsilon, but the noise sensitivity noise rate rho of any linear threshold function is square root rho. It's this cute, clever argument. And if you work through, you know, the relationship between noise sensitivity and Fourier concentration, it gives you this really lousy algorithm for learning linear threshold functions, like n to the 1 over epsilon squared time to learn to accuracy epsilon just under the uniform distribution. So you're like, oh my God, why would you want to do that? I could have learned in poly-n time, like under any distribution. But the point is, it works not just for linear threshold functions, it works for intersections of linear threshold functions or arbitrary functions of linear threshold functions. Got some k hunter, you feed k different LTFs into it. Well, this noise experiment, it's a trivial union bound, right? The probability that a noisy input crosses any of the separating hyperplanes for your k LTFs, you can, you know, you just do the same analysis you did before. So it's a very, very bad approach to learning a single linear threshold function, but it gives us the state of the art for learning kind of juntas of linear threshold functions or intersections of linear threshold functions under the uniform distribution. Okay. Some other results along these lines, if you're
I'm
interested.
sorry, can I quickly add, is the root n over epsilon thing tight, the Fourier thing for monotone?
Yes.
Okay.
The dependence on epsilon is known to be tight.
Epsilon.
I think they're both tight, yeah. There are lower bounds even for so-called K monotone functions. If you have functions where like, it's like an XOR of like K monotone functions or like K sign changes as you walk up the cube. We know things like that as well. Okay, so, yeah, sorry, if you want a different class or going a little bit beyond AC0, if you have a linear threshold function on top and you have AC0 circuits feeding into it, there's an asterisk here and there's you or one of the authors of this result, because like the story is not quite complete. This so-called Gaussian-Lineal conjecture, a conjecture about the total influence of degree D polynomial threshold functions. Daniel Kane, who's not in the room, but is maybe somewhere nearby, has, these great results on almost proving the Gaussian-Lineal conjecture. The Gaussian-Lineal conjecture says if you're a degree D polynomial threshold function, your total influence is at most D times square root n. And Daniel has very good results, which get you something close to that, but don't quite get you that. If you got that result, you would have this running time for LTF of AC0, depth D LTF of AC0. As it is, we have slightly weaker results, but once you finish Daniel's efforts and really prove the Gaussian-Lineal conjecture, this would be what we would get. And we're going to come back to this running time again in the context of this learning with non-trivial savings. And okay, good. So if you say, what are the challenges in uniform distribution learning? The real central challenge in uniform distribution learning, if you don't have membership queries, is the Junta problem. We'd like to learn DNFs well, we'd like to learn decision trees well. You have to go through Juntas to handle either of these classes. So probably everybody here is familiar with this, but just in case, like what is a K Junta? A 3 Junta is a function which depends on exactly 3 of the input bits. A K Junta is a function where there are n minus k relevant variables and k variables that the function actually depends on. Question?
I think I saw somewhere there is a paper called the Gaussian-Lineal conjecture was false.
By Bernard Chapman.
And it was like,
It's that's for like a very finicky version of Gaussian-Lineal that doesn't rule out like big O of D root n. Yeah, there is this thing, the Gaussian-Lineal conjecture is false. It's like a 7 variable function where degree 2 polynomial or something like that. It doesn't rule out like the asymptotic form of the conjecture that we think about. What those guys originally conjectured, Gaussian-Lineal, was that like you just take like n choose n over 2 plus n choose n over 2 plus 1 plus n choose n over 2 minus 1. Like you take the D middle layers of the hypercube and those are the edges those are the like cutting all of those edges is exactly the best thing to do. With a degree D PTF. With degree D, you can slice the D layers of the hypercube. And like that conjecture, you're right, Bernard Chapman has a thing saying that is false. But what we care about is just the asymptotics. Is it really D times root n times 2 to the n as the number of edges you can slice? So they, big O D times root n times 2 to the n number of edges you can slice. We don't know if that's false. In fact, given all the Daniel Kane's amazing results, probably true, but it's not clear what anyone close it yet. Yeah. Yeah, that's a good find. That's a good find. I think I'm chatting paper. Sorry, yeah. So Juntas, K Juntas, right? So if you want to learn a K Junta, it only depends on K variables. So a brute force approach, you could just try all possibilities for one of the K variables and learn in time like n to the K or something. And people have worked fairly long and hard on this problem, and it's a big open problem. I think Avram Blum is like on the record that he has to give you $500 or something if you can like learn K Juntas and n to the K over 2 time. Take it from me, there are much easier ways to make $500 than doing this, but people have made progress. So the state of the art is this Greg Valiant paper where he uses this like clever insights on the light bulb problem and finding correlations in subquadratic time and so on to get like n to the 0.6k. But like we can't even get n to the k over 2. We have no idea how to get into the little o of k. But this is kind of where I would say the frontier of the challenge problem is for uniform distribution learning if you don't get membership queries.
What do you think of K as a function of that?
Could be anything. Just think of it as like parameterized complexity. Just think of it as its own parameter, which can be large, but it's independent of n.
I want to just copy a question from an earlier audience member.
Yeah.
Are there any fine-grained complexity results about learning K Juntas in K?
In this uniform distribution setting, I don't think so, but I'm not 100% sure. Yeah. Yeah. There are some kind of some connections to parameterized complexity, but I can never understand those papers. So, I'm pretty sure that they don't telling you things about the uniform setting. Okay, so now we're gonna have a good time because now we're gonna talk about the most powerful model with the weakest requirement on success. We're gonna give ourselves the power of membership queries, and we only have to learn under the uniform distribution. Okay, so we're clearly gonna learn polynomial size circuits in this model. Just kidding, of course, we're not gonna learn polynomial size circuits, but you can do things that you couldn't do in the other models. For instance, the celebrated result of Jeff Jackson from the late 90s, he could learn DNF, like flat out learn DNF. You have an S-term DNF, he learns it in polynomial in S and 1/epsilon. And it's really nice. It's uses crucially these like boosting algorithms, which have this extra property called smoothness. Russell's going to teach us all about smooth boosting in different contexts, maybe this afternoon. It uses Fourier technology like the Goldreich-Levin algorithm or Kushlevic-Mansour's version of the algorithm to find large Fourier coefficients. We crucially seem to need membership queries to do this. So this is like, it's, it's almost 30 years old. I think of it still as like a kind of a jewel of learning theory. It's really nice.
So this is going off on a tangent, but in around 97, I had heard of this thesis and I was teaching like an advanced theory course. And I said to myself, I always teach the same things that I know, right? So I'm going to teach something completely different that has nothing to do with anything that I've taught before. So this is what I picked. And there were like 3 ideas. The first idea involved like, the Fourier representation of DNFs. And I had already talked about Fourier representation. And then I said, oh, how about the second idea? Oh, you said, Kushlevic-Mansour, but it's also the Goldreich-Levin algorithm. And so I'd already taught that when we were talking about cryptography. And then I said, well, there's a third idea, smooth boosting. What's that about? And it turned out to be the hardcore distribution lemma.
That's how you get into the hardcore distribution stuff.
So that's how I realized.
That's cool.
Yeah.
So,
So,
I thought you were gonna say, so you gave like learning DNF as a homework problem.
no, I did teach it, but it was a lot less. In fact, like almost all the concepts I already taught in the course were totally different motivations.
Oh, that's cool. That's interesting. I didn't know that was that was what brought you like the hardcore lemma stuff?
No, I'd already done it,
You've done that, or, yeah.
but I didn't know what I was doing.
Good. You and me both.
Yeah.
Good. Okay. Yeah. So this is a great result in the uniform distribution setting, and it's it's nice evidence that like it makes us stronger. Another nice result, I think, really nice result. I like this result a lot. Is remember if we were trying to learn any function of k-linear threshold functions, so like a k-hunter with LTS plugged into it, in the setting without membership queries, what we had was this like n to the k over epsilon squared kind of thing. That was by this noise sensitivity, blah blah. If you get the membership queries, you can kind of use like techniques from automata learning with techniques which arose in like the complexity theory de-randomization context. You have a single LTF, you can approximate it under the uniform distribution by a small branching program, a small monotone branching program, right? Because think of like an LTF, it's got all these positive weights. As you satisfy more variables, you're just upping the state. The state only moves in one direction. The state is like the sum of the weights that we've picked up so far with the variables you've read so far. So LTFs in general, you want to write an LTF as like a branching program or monotone branching program, and it's size 2 to the n. If you want to approximate an LTF with a branching program, you can do it in polynomial size, inverse polynomial accuracy. And so you combine these like approximation ideas, which arose from, work again on pseudo-randomness with like, angling type ideas on automaton learning, and you can get this much, much better result. So, epsilon went from like, instead of having like epsilon squared in the exponent, epsilon goes down into the base. So again, it's like a very different kind of approach. The membership queries give you like a lot more algorithmic power. You can do more interesting and powerful things. Yeah, perhaps the greatest learning result of all time, and I'm not just saying that because the organizers are why I'm here, is this CIKK paper where they learn AC0 circuits augmented with like mod P gates. I am probably the 10th most qualified person in this room, maybe the 20th most qualified person to talk about this, but from what I understand, it uses natural proofs. And so Vigderson, this is like it's kind of amazing. And this, but we'll see like this was this really like embodied this theme of like trying to get non-trivial learning algorithms, something I'll talk about in the remaining part of the talk. You know, one of our goals, the last part of the talk is going to be, hey, how can we get non-trivial learning algorithms from like complexity theoretic techniques? But the kind of non-trivial learning algorithms that I was thinking, oh, you might be able to get from like lower bounds in complexity theory or these pathetic things like 2 to the n minus something in the exponent of the n. These guys are heroes. Like, you know, they got quasi-polynomial time, you know, for this rich class by sort of having deep insights about like, you know, the lower bound techniques. So I don't know how you did it. I wish you would do it again in some of the other classes, but yeah, so.
We were the giants before us.
You want to have those giants you can bring in. So two things that we don't know how to do, even in this setting where we have a lot of power, we have the membership queries, and we only have to learn under uniform. We don't know how to learn, say, depth 2 majority circuits. So low weight LTF with low weight LTF. We certainly have lower bounds for this class, but we don't know how to learn it non-trivially, even under the uniform distribution, even given membership queries. You know, maybe you could hope to do AC0 in really polynomial time in this model. I'm giving you membership queries. We can do AC0 depth 3. Sorry, let's just talk about depth 3 in n to the log n time without the membership queries. Maybe the queries, you know, should do a little bit better somehow, but we don't know how to do that. How much time have I left? Okay, so I can get to the third part then, learning non-trivial things. Any questions?
I have a provocative question before the last part. Would you say, so for all of the other learning settings, you gave us like a key tool and some ad hoc theorems.
Yeah.
For PAC over uniform with membership queries, is it fair to say that the key tool is sort of like rummaging through the junk drawer of complexity? Or is there something else like going on?
I love that phrase. I think it qualifies as a tool for a second.
Yeah, right, like
Yeah, I mean, it's kind of like, you know, the way I would think about these things is, the richer the framework is algorithmically, the more you can do, the less likely it's gonna be that there's like one hammer to hit it with, right? But yeah, I do think that like, you know, if somebody puts you on a desert island and says you don't get off the desert island until you solve some of these open problems, you wanna open up your complexity proceedings, and you want to start thinking about complexity rather than algorithms, probably. I think Ellie was first, and then Russell.
Oh, it's actually a comment related to that comment. I mean, it's wondering if like there's a backwards loop. So you mentioned CIKK. I'm nicely surrounded by them. So I can ask the question. So there's like a reverse direction to that, which is basically all those facts that you just presented. You can actually get natural properties out of them.
I'm gonna pass that to CIKK answer rather than.
Well, I mean, this is not a question. That's like a fact. The question is like, does it give you something interesting? Like we can get like natural property, so we can go back, rewatch your lectures and say natural property for this, for that, for that, for that, for everything that you just mentioned.
You're saying, does it give you like new insights or a more direct way to understand these things?
Maybe it's just to do with this. How did you call it, Marco? Valiant complexity, or what was the term?
Rummaging through the
Yeah, so you can think about this rummaging, maybe like, okay, you can take all of this back learning and uniform distribution, blah, blah, blah. Each one of them gives rise to a natural property. Maybe this is your like sledgehammer or something like that.
Just before you go on to the next topic, as a preface to that, you said that 2 to the n is the trivial learning algorithm. And so you're trying to beat that by a small amount.
Yeah, that's what the next part's gonna be all about, yeah.
This is a very, very forgiving audience. So we'd actually be interested in learning results that spend much more time than 2 to the n. As long as they kind of distinguish between having like, if it's a proper learning algorithm.
Yeah.
And it gives you something as a result, because we're trying to just distinguish between things that have smaller descriptions and things that don't, and we're given the whole truth table. You might want to think about failed approaches and see whether your failed approach to give an improved algorithm is actually a good approach to give some version of FCSP.
I see. I think I need to come to a better understanding for myself of like what would suffice for different problems. setting, like, I'm very much in the learning mindset, where like, you give me 2 to the n time, all right, I'm gonna run the world's least inspiring learning algorithm of, building a truth table and so on, but you're saying you don't want.
I don't want you to output
I
the
can't
truth
output
table,
it.
you have to compress it a little bit.
Right, okay, I'll talk about compression a bit in this.
Yeah, yeah.
Yeah, okay, so you're saying like, you could go back and revisit lots of things in learning where you're like, you just try to compress and you get,
Yeah.
That's interesting. Yeah, that's a good question. We'll talk about compression now. So, yeah, maybe with this forgiving audience, I shouldn't abuse this audience by saying we're lowering our standards, we're abandoning our dignity, but the kind of thing that I want to talk about now is the kind of thing which would not be viewed, by most people in learning as like interesting learning, right? But the point of view we're going to take is that it is interesting to learn in time better than 2 to the n. I achieve any kind of non-trivial savings and I've done something. Okay, so it's a perspective you can have. It's probably not going to get you the best demo award at NeurIPS or whatever, but it's interesting for people like us. So this is not a completely new point of view. Igor Oliveira or Santana had this nice paper. This is this conspiracies paper, where they establish conditional results. They say if you can do non-trivial learning in this framework, better than 2 to the n over n, then you can do it significantly better, 2 to the n to the epsilon kind of thing. They have equivalences between different frameworks. They get some lower bounds for non-trivial learning and so on. In this talk, I'm going to really just focus though, again, like algorithms, same kind of spirit of what I've been telling you, this is the fastest we can do this, this is the fastest we can do this. So in the remaining results I tell you about, they'll be like results I know about for these non-trivial learning kinds of problems, algorithmic results. And I probably don't have to justify this in this audience, but it's not like this is a completely crazy perspective. It's a weird perspective for like, hardcore learning-ish people, but for satisfiability, for exact counting, we're interested in like, when can you get a little bit of the savings over brute force, right? And we've seen celebrated results in complexity. This can be very useful in settings. This really doesn't matter, but if you want, you can think about this. Maybe it's nicer to say, I'm going to think about this in the online setting. There's no epsilons, no deltas, no nothing. It's all just about 2 to the n, doing better than 2 to the n. You don't have to be like, oh, what if epsilon works in very high accuracy epsilon is, how does that come into the picture? So we can think about this kind of learning as being like a harder problem, a more demanding problem than compression. So what is a compression algorithm? It's on the screen. A compression algorithm is an algorithm, as I understand it, where you're given a 2 to the n size truth table for your function. Your algorithm is supposed to run in polynomial time, so that's in 2 to the O of n, because the input is of size 2 to the n. And you're supposed to compress. You're supposed to output a non-trivially small circuit, a circuit that does better than, this is Lupinov, Shannon, I always get this mixed up. Lupinov, okay, you're supposed to, compress it to a non-trivially small circuit. Learning is like this, but it's harder in, I guess, 3 senses. I don't give you the truth table. I give you maybe random examples or counter examples or the ability to make membership queries, but it's not like I dump the entire truth table on you. You're supposed to run in non-trivial time, so faster than 2 to the n. Like time 2 to the 5n is not enough. You guys are very forgiving, but in the learning context, we want something strictly better than 2 to the n. And if your algorithm ran in time 2 to the n minus some savings, the output will certainly be a circuit of size at plus 2 to the n minus that some savings. So, if you can learn the concept class, you can compress the concept class. Yeah, that's a stronger requirement. Okay, so, can we get beyond these like red barriers, these things that like we're, where we don't know how to get learning algorithms from the standard perspective of wanting, 2 to the square root n or polynomial time or something like that? The answer is yes. And I'll just briefly talk about a couple of results in this paper where it was really kind of like a proof of concept. We had like, oh, here are some kind of initial observations about doing things in this way. So the first technique was stolen from CIKK or borrowed from CIKK. It's that if you can do uniform distribution learning, although you need the dependence on epsilon to be good, and we'll see that quantitatively in a second, this gives you learning with non-trivial savings. And again, it's because we sort of don't have a particularly high bar here. It's really an extremely simple idea. So you've got some learning algorithm. It runs in time t of n, one t of parameters n, 1 over epsilon. It's a uniform distribution learning algorithm. If you ran it, you would run it this much time, you would get an epsilon accurate hypothesis out. So you can think of this as like something you could do with membership queries. With membership queries, I can query random points, and I can simulate access to this like random oracle, this uniform distribution oracle. And then, okay, you're at the point where you have an epsilon accurate hypothesis, well, why not just patch it up, right? There are only epsilon times 2 to the n many points where you're wrong, so make an equivalence query, and if you get a counterexample, you know, throw 3 gates onto your circuit and be like, if it's this exact input, you know, I know what to answer, and then do it again, and do it again. Okay, so this will be like epsilon times 2 to the n time to just patch the epsilon 2 to the n many mistakes. So you trade off epsilon, you trade off these 2 parameters, you say, okay, I'll choose the best epsilon, which makes the overall running time as small as possible. And you can see that in order for this to be a useful technique, your t of n1 over epsilon, your running time of the uniform distribution learning algorithm, it better not have too lousy a dependence on epsilon. If it does, this isn't gonna work. Okay, so we can kind of go through this with a couple of examples. I mentioned this result, it was Gopal, this is GKM actually, Gopal and Climb, so I wrote that wrong. We saw that, you know, these guys, if they're in the uniform distribution setting and they get membership queries, they can learn any function in an intersection, or could be any function of k half spaces very quickly in time, you know, with a nice dependence on epsilon. It's like k over epsilon to the k essentially. And if you plug in a running time like that into this, you get really, you know, a nice savings. You get a linear savings if k is a constant. Okay, you'll do, you know, 2 to the 0.9n if you're learning an intersection of 8 half spaces. Yeah.
I'll get you why to understand that. Previously, you said we should looking at the own equivalence query, and now you're talking, in this case, you talked about membership query, so which one?
So I'm learning with the uniform distribution plus membership queries.
Okay, because,
Yeah.
okay, previously, you said, we should think about this, equivalence online queries.
Okay, I'm not sure what I said, but sorry about that. Yeah, no, the model, so okay, let me be straight here. The model that we are in, okay, yeah, I think I understand your question, the confusion. We are trying to achieve, we're trying to achieve, where did this go? OLMB, yeah, we're trying to achieve exact learning. So we're trying to achieve like perfect accuracy. Some of our algorithms will require membership queries as well. Yeah. And like for this technique, if your technique is, oh, I'm gonna like do uniform distribution learning and then patch it up. To do uniform distribution learning, I think you need these membership queries because I need to be able to get uniform random examples. And if I just have the counterexample oracle, they may not give me uniform random examples. Yeah.
If our goal is compression at the end, then, which I think is probably true for this side of the audience.
For this audience, yeah.
Then pretty much any reasonable notion of query is allowed, right?
Yeah,
Because,
you got-
you have access to the whole truth table
truth table,
when you're
yeah.
doing compression.
Yeah, makes sense. So, yeah, this is just, I mean, I know you guys all know how to minimize a function like this for depending on what t is, but just to go through a couple of examples, you know, sometimes this works really well. Like if your epsilon dependence is very good, like it is for intersections of half spaces, you get a nice savings, right? There's a big savings, n over k in the exponent, right? We saw the LMN algorithm for learning AC0 depth E. Okay, we have a log 1 over epsilon in the exponent, and you work it out, and you still get a pretty good savings. N over log n to the d. So the savings is going down because the epsilon dependence of the uniform distribution learning algorithm is getting worse. CIKK, I think this was your epsilon dependence. It's like log n over epsilon to the power d. If I'm correct about this, then it means the savings you get is, you know, it's still non-trivial, but it's smaller because we don't have as good an epsilon dependence. And if you think about a class like this, you know, LTF of AC0, and we saw that the dependence there, this is the result that you're going to prove once you finish Daniel's work on the Gaussian lineal conjecture. You know, there the dependence is not very good on epsilon. It's like 1 over epsilon squared in the exponent, and you don't get anything. Right? You would get a saving. You get something like 2 to the n over root n, which is not a savings. Okay. So, okay, this simple trick can only get you so far, but if you think a little bit harder than just using these uniform distribution results in a black box way, you can sometimes overcome these things. So we'll see that we actually can get a decent savings for LTF of AC0 with this other technique, which is based on random restrictions. Okay, So please do not look at the right-hand side of the slide, look only at the left-hand side of the slide for now. What's going on the left-hand side of the slide? Well, let's say you're starting with an LTF of AC0, okay? So you're feeding a bunch of AC0 circuits into a linear threshold function. Imagine you hit it with a random restriction. What does the switching lemma tell us happens? The switching lemma tells us that, with very high probability, each of these AC0 circuits collapses to a shallow decision tree. So my overall function becomes a linear threshold function of decision trees. Okay, and this is, in other words, this is a low degree PTF, because, any decision tree we saw, decision trees are low degree polynomials. I'm taking a linear form, linear threshold of low degree polynomials. Okay. Good. Now please look at the right-hand side of the slide. So this is a different way of looking at it. I'm drawing the Boolean cube for you here. That's this diamond. You've got your function f on the cube. You do your random restriction, but I want you to think of doing the random restriction as you pick the variables that survive, the set of stars. And you imagine all assignments to the variables which are getting fixed, not just like one assignment. If you do that, it really corresponds to, looking at the original domain, the whole Boolean cube, and you think of it as getting like partitioned into a bunch of little Boolean cubes. Okay, the little Boolean cubes have dimension corresponding to the number of variables that you didn't fix, the number of stars. So what does the switching lemma tell you now? It tells you that on most of these subcubes, okay, you collapse. The function becomes an LTF of decision trees, i.e. a low degree PTF, which is very efficiently learnable. Remember, standards are really low. We just want to learn over a given domain in time significantly faster than the number of points in the domain. And in a setting where you actually get this collapse, you're definitely doing that. You're getting a big, big savings over brute force by learning these low degree PTFs. That's only time into the D, much, much better than like a brute force thing. On the other hand, the switching lemma has a failure probability, so you don't achieve this on all subcubes, you achieve it on most subcubes. You're unlucky on some subcubes, guys like this, and what are you gonna do? You're gonna do brute force. You just make membership queries on all the points in the subcube to learn it in brute force way. Okay, so you can trade these things off against each other. You trade off the failure probability of the switching lemma against the, number of, which is like, tells you about like the number of subcubes where you're making mistakes. The right thing to do is to use one of these multi-switching lemmas, either Russell's work with Matthews and
William Matthews in a moment.
Okay, yeah, like either that multi-switching lemma or Johann's multi-switching lemma, you work this through and you trade the parameters off against each other and you do get like this pretty good savings even for like LTF of AC0. So, what's the lesson here? It's a lesson we all know it pays to like open up the proof kind of and look at what's really going on to get you the uniform distribution results. Yeah, so that's the second technique that I wanted to tell you about. The third and last thing I'll tell you about, do I have 3 more minutes?
Yeah, fine.
Okay, great. The third and last thing I'll tell you about is an approach based on like Nechi-Peruk. I don't know how to pronounce that word. Nechi-Peruk? Okay. Now I feel insecure about it, but Nechi-Peruk style, like lower bounds. So what is the idea of like the Nechi-Peruk lower bound framework or lifestyle? It's basically that like, if you have your function and you partition the input variables into disjoint buckets of variables, okay? If the sort of this way of measuring the number of sub-functions, or sometimes people write like the sum of the logs, or you're just writing the product of the number of sub-functions. So in the first bucket, like this num fs1 means you fix all the variables outside of bucket s1 in all possible ways, and you count how many distinct functions do I get under all those restrictions. Okay, that's num fs1, num fs2, num fs3, so on and so forth. Nechi-Peruk tells you that if the product of these numbers is very large, then you get a lower bound in a range of computational models. It's a complex function in terms of formula size, branching program size, switching network size, blah, 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 blah. These kinds of things, okay? So all we're gonna do is we're gonna take a contrapositive view on this statement, right? If we contrapositivize this statement, it says, well, if f is not too complex, then if I take any, equipartition of the variables, just think of it as divided into equal size blocks, one of those blocks must have not too many distinct subfunctions, right? Even as I change all the fixed variables outside the block in all possible ways, I don't get that many different functions. So that should be good for us, right? If I'm getting much, much less than, the maximum possible number of subfunctions, intuitively that should be useful for learning with non-trivial savings somehow. And it is useful for learning with non-trivial savings. I don't want to go into all the details on how you do this, but you can use something like the halving algorithm, or some amortized version of the halving algorithm. Basically, you just try all restrictions of the variables outside the blocks. And you'll find, the first time you certainly find a new function, you have to search, you have to brute force learn the function. And then you're like, oh, maybe this is the only sub-function that ever occurs. So you run the halving algorithm over a set of one function. And it probably will fail, you'll brute force it, you'll find a second function. If you found J functions so far, when you're trying that next block, that next assignment to the fixed variables, you say, I'm just gonna run the halving algorithm over this assuming that I've found all the functions, which it could be. I think you need this sort of amortized version of the halving algorithm, which is not too difficult. You can make it work.
What is the halving algorithm?
Good. Halving algorithm is just this approach where if you have a concept class with, say, n concepts in the class, and it's over a domain of size n, you can learn in time n times n. You're just learning a function in time the size of a matrix of like examples and labels of the concept class. So if you, the idea here is like, if you were to run, imagine you want to run the halving algorithm many times to learn different functions from a class. If I wanted to run the halving algorithm naively z times, well, each run takes me nm time, and I'm doing it z times, it would take me nmz time to run it, z times. It turns out that with a little bit of pre-processing, you can do some slightly expensive but not too expensive pre-processing, and then you can run the halving algorithm super fast. Each of the z runs, you can run it in time polylog the size of the matrix instead of linear in the size of the matrix. And that's exactly what we're doing here. We need to run the halving algorithm over and over again because we have all these different, the concept class of like all these different restrictions to the fixed variables. So yeah, maybe this is too much detail for the last minute of the talk. Bottom line, if I tell you that, there are not very many distinct subfunctions on which leave a fixed set of variables free, I think it should be intuitively plausible, but like you can get some non-trivial learning in that kind of setting. It's just not.
When you do something like just do some random samples and see if they match one of your functions on your list?
Yeah, that's actually something like that is part of how I think you actually implement something like this. There's something,
Okay.
yeah. Yeah, so when the dust settles, you get basically for all these classes where we have Nechi-Karuk type lower bounds, you get not learning with some non-trivial savings, like some polynomial savings, the epsilon kind of thing. So I think I'm out of time and I'm basically done. Just a couple of points of questions for future work. I go through this and I'm done. I think it would be really nice to do non-trivial learning from other lower bound techniques. We saw random restrictions give us something, Nechi-Karuk gives us something, like there are polynomial based lower bounds that we all know and love. It would be interesting to try to get non-trivial learning, by kind of mining the ideas in those lower bounds, or like, Rasburov style thing for monotone functions. It'd be interesting to do that. Oh my God, like CIKK totally, harvested like natural proofs and some Wigderson types of lower bound ideas and ingredients to get like, it's too good to qualify for what I'm talking about. It's quasi-polynomial time instead of like learning with some miserable savings. But I think this is like a really interesting direction to pursue, or you can try to be as ambitious as CIKK, or you can just try for non-trivial savings. I would think there should be other non-trivial savings results that can be gotten. There's some work by Ari Kotchmer fairly recently for like an agnostic setting where I guess he uses, I don't know much about this, kind of Masson flavored communication complexity type natural proofs. But so yeah, I think there is evidence that you can do things along these lines, but there's probably more to be done. Yeah, and then I think just, kind of, if you're like, oh, I really want to get non-trivial learning, we should have non-trivial learning for some concept classes where we don't yet have it. If you have an intersection of n squared type spaces, right? It's a trivial concept class to prove lower bounds on. You certainly can't compute parity unless I give you an intersection of 2 to the n minus 1 many half spaces. So, but we don't know how to turn this easy lower bound into a learning algorithm or something like De Morgan formulas. Valiant and his co-authors had results on learning an extension of like De Morgan formulas. Is this correct? De Morgan formulas of size almost n squared with XOR gates also at the bottom. But we have great lower bounds for bigger De Morgan formulas of size almost n cubed. Of course, it would be interesting to try to get learning results there. I don't know how to do that, but I think there's room for future work here, and I think that's really everything. Yeah. Yeah.